So the question is, why do we need a new 3D API? What was wrong with our old 3D APIs? Well, OpenGL is old. That's no reason to replace it, but it was, just to give perspective, released in 1992. The Mesa OpenGL implementation started in August 1993. So in about 24 years of development, it's done well. It's survived pretty well over those years, but computers have changed, how stuff work has changed, and the OpenGL design. Oh, did I lose my slide? Ah, yeah. Why have I got a blank slide in there somewhere? Oh well. So the OpenGL design has a problem. It was designed in 1992 for a start, and that was based on the hardware at the time. It has a very big state machine hiding inside it, and that state machine has just grown with new hardware and new extensions, and people add more things to it, and it just got bigger and bigger. There was a vague attempt to reset this about OpenGL 3 time. If you want to look at the history of that, that failed miserably. It wouldn't have been perfect, but it would have been a lot better than where we ended up. But due to the momentum at the time, people still wanted to keep all of the old APIs that were in there, doing all of the old immediate mode. I have to type everything in, for every vertex, one line by a time. Yeah, it's sort of struggling under its own weight now, and it's gotten hard. So that's a lot of legacy functionality that hardware doesn't even support is in there now. So then you have to emulate that on modern hardware just to support some feature that maybe no one's even using anymore. But to get conformance, you have to get through this. If anyone's ever programmed OpenGL before, you'll be aware of the OpenGL context model. So you create a context, you do everything inside the context. When the context needs to send stuff to the graphics card is undetermined. You'll do draws, and some of the times those will get sent to the graphics card. Sometimes they'll just sit in a queue. You can call GL flush when you want to explicitly do it, but you have no idea when it implicitly happens. It could implicitly happen at any time when you're building your context and putting your state out there. So it hides a lot of the GPU details from the applications. A lot of the control flow things are hidden from your application. You don't get to see what's actually going on. So the problems that design has caused. Having this single context thing makes multi-threading really difficult, because one of the rules of OpenGL is the context can only be bound to one thread at a time. But if you've no idea when that thread is going to be getting stuck into the hardware, explicitly pushed down, it makes it really hard to run multiple threads in parallel with multiple contexts. The sharing model is really arcane, and a lot of the drivers don't always get it perfect. So yeah, you pretty much end up with a lot of OpenGL games are very limited to either a single thread, and the driver does a bunch of tricks internally to multi-thread it. But multi-threading the API is really hard, because the API has a load of, I'll give you a block of memory, and when you return from this function, I want to override it. So you have to copy a whole lot of stuff if you want to stick stuff into another thread. So there's a whole lot of, a lot of hacks in graphics drivers to try and get some sort of threading of OpenGL, just so it can use all of the cores on your machine, which, we've had a lot of cores for a long time. Sharing the context isn't always reliable. It can be a pain in the ass, and you can bind something in one thread and forget to, and then things fall over. It's really hard to debug. Even another way, so OpenGL is also, the original OpenGL was always designed around a window. You had to have a window. If you wanted to render off-screen, they added these frame buffer objects later for doing off-screen rendering, but you still need to have a window. And then eventually it grew, you can maybe get rid of the window, but it's off-screen rendering isn't really native to the design at the start. So it's sort of been bolted on, and a lot of people want to do off-screen rendering. That's what, it's a thing that people like. GPU hardware has converged. When OpenGL came out, there was many graphics card vendors. Nowadays, at least on x86 side, there's possibly 3. On ARM, 5 maybe, I suppose. But they're all converging on a similar model. They're all designing their hardware around OpenGL ES or OpenGL Direct3D. So there's not so much of the crazy offshoots with insane things that OpenGL needs to support or hide from you. So there's not as much need to hide the details of how the GPUs work from the applications. So this gives a bit of a comparison between how things look from OpenGL to Vulkan. You'll notice in the OpenGL side, the applications at the top, it's not huge. The driver is big. The driver takes care of all of the memory management, the error handling, the context handling. Can't read the small writing, but yeah, the complex drivers, everything's in the driver. That's where the complexity lies in a lot of cases. And it makes it kind of hard for us to evolve things because the drivers are so complex. The error handling is always active. There is an extension now to turn the error handling off. We haven't actually put that into open source drivers yet, but it's again a bit of a hack on top of things. It's just, oh well, we'll just try and get rid of this problem because we need to. The shading language, so GLSL, it's fully pre-processed. You have to get the GLSL shader into the driver, run like a CPP equivalent over it, and then do a full compilation. It's a C-level language. So there's a lot of flexibility in what GLSL expects and what way it should work. The spec isn't always exactly clear on what should expect. So but it's also very complex. So every time you get a shader, you have to pre-process it, and then this leads to complex caching models and ways of hiding the overhead of compiling and pre-processing the shaders, and again, more complexity, and further away from what the hardware's doing. But the Vulkan model moves a lot of responsibility back up to the application. In reality, it's probably not going to end up in the game. It's probably going to be more of a toolkit problem. So your Unity or your 3D or one of those Source 2 engines, the engines are going to be the thing that takes the complexity, not really the application. I think most games will be sort of targeted still to run on GL and other things, but they'll have an option. But what does the application have to do? It has to take on the memory management, for example, is now the application's responsibility. The application knows how much video RAM you have, knows how much RAM you have. It needs to decide how to do things. Threads, the application can happily run as many threads as it wants, and it's in charge of those threads. It decides what gets sent to the graphics card when. There's no implicitness in it. It's, I wish to send this to the graphic card, send it. There's never a, oh, when you said that draw, I ran out of space, so behind your back, I sent it all to the graphics card and started again. That's all gone. Everything is explicit. Moving stuff between threads, giving different threads access to images, everything has to be explicitly stated. There's transitions all defined for everything. It exposes all of the hardware queues. So if you look at your standard Radeon graphics chip, it probably has one graphics queue, 8 compute queues, and maybe 2 DMA queues. In OpenGL, they're sort of all hidden, and the driver will use them if it feels like it, or maybe if the moon is the right size, it'll go, I'll just do this with DMA transfers today on this chip. But there's no way for the driver to, or for the application to control that. So if you know that the transfer path is faster, you can't influence how that gets used. So Vulkan gives them access. It exposes the graphics queue, the compute queue, and the transfer queue, and it lets you know what you're allowed to do on those. So graphics queues are generally allowed to do graphics. All of the 3D API, all of the operations are there. The compute queue is pretty much limited to just a compute operation, so it's usually a subset of the graphics queue. And then the transfer queues are limited to just moving stuff generally between images and buffers. Yes, there's a lot more for the app to do. Even a trivial app is quite an undertaking to write. A properly triangle drawing app is still a lot of work. But the idea is by giving this power to the applications, we will reduce the CPU overhead, and we can use all of the threads on our 8-core chips, and games can get much faster. It's sort of similar to where consoles had gone over the last while. So consoles have had this sort of model where they've got a, I think the PS4 CPU is weak, but because they're designed around the GPU is powerful, we don't need that much CPU, we don't have all these overheads. It also enables other models that we couldn't do with GL. One thing that you may have heard of is asynchronous compute is a thing that happened with DirectX 12 and Vulkan. With AMD's graphics cards, if you were throwing stuff down the graphics queue and you weren't using all of the all the units on the card, if you threw stuff into the compute queue at the same time, it would use the spare pieces that were left over the graphics queue wasn't using and do the compute jobs on them. So